A function is like a small machine. You feed it some inputs, it does work, and it may give you an output. In most compiled languages, C++, Java, you have to tell the compiler two things: what the function looks like, its declaration or prototype, and how it works, its definition. The declaration only states the return type, the name, and the types of its parameters, ending with a semicolon. Example in C. Int max int a int b semicolon declaration prototype. The definition provides the actual body surrounded by braces. Int max int a int b left brace definition return a greater than b, then a else b semicolon right brace. If you write the definition before any call, the declaration can be omitted because the compiler has already seen it. In interpreted languages like Python, you only need the definition written with def. Def max a comma b colon return a if a greater than b else b. The key idea is that the declaration is a promise about a function's interface, while the definition fulfills that promise with actual code. When you give a function a value, the language must decide how the value is handed over. Pass by value makes a copy of the argument. Think of photocopying a sheet of paper and handing the copy to the function. Any scribbles the function makes stay on the copy, not on the original. Void inc takes an integer x. Inside inc x is incremented, which only changes the copy. In main, an integer a is set to 5, inc is called with a, and a remains 5 after the call. Pass by reference gives the function a direct line to the original data. It's like handing the original paper instead of a copy, so any changes affect the source. Void inc takes a pointer to integer x. Inside inc, the value pointed to by x is incremented, modifying the real variable. In main, an integer a is set to 5, inc is called with the address of a, and a becomes 6. Void inc takes an integer reference x and increments x. Python's model is often described as pass by object reference. Mutable objects such as lists and dictionaries behave like pass by reference, while immutable objects such as ints and strings behave like pass by value because the function cannot alter the original value. Understanding which method a language uses is crucial to predict whether a function can modify caller data. Explanation: every function must state what kind of value it will hand back to the caller. This is the return type. If the function does not need to return anything, you use the special type void or none in Python. Int add open parenthesis int a comma int b close parenthesis open brace returns an int return a plus b semicolon. The value travels back to the caller close brace. Void print sum open parenthesis int a comma int b close parenthesis open brace returns nothing. Print %d newline comma a plus b close parenthesis semicolon. No return statement needed. Reaching the closing brace ends the function close brace. A function can have multiple return statements, but only the first one that executes ends the function immediately. This allows early exits when an error is detected. Int divide open parenthesis int num comma int den close parenthesis open brace. If den equals 0, return -1 semicolon. Error code. Stop here. Return num divided by den semicolon close brace. In languages with type inference, for example Python, JavaScript, you do not write the return type, but the concept remains. The function either sends a value back or finishes silently. Variables inside a function have 3 related properties. Scope, where in the program the name can be seen. Local variables are visible only inside the block braces where they are declared. Global variables are visible everywhere after their definition. Lifetime, how long the variable exists in memory. Automatic stack locals are created when the function is entered and destroyed when it returns. Static locals keep their value between calls, existing for the whole run of the program. Visibility, similar to scope, but emphasizes that a name can be referenced from a certain region of code. Analogy: think of a toolbox. A local variable is a tool you keep in a portable toolbox you open only while the machine function is running. When you close the toolbox, the tool disappears. A static variable is like a tool bolted to the machine's frame. It stays there for the next time you turn the machine on. C code, define a function named counter that returns an integer. Inside the function declare a static integer variable calls initialize to 0, which lives for the whole program and remembers its value. Increment calls by 1, return calls. If you also declare a global variable, C code, define a global integer variable named global total initialized to 0, which has global scope and a lifetime for the duration of the program. Any function can read or modify global total, but good practice limits such use to avoid hidden dependencies. Recursion is a technique where a function solves a problem by calling itself with a smaller or simpler input. The essential ingredients are: recursive case, the part where the function calls itself; base case, a condition that stops further recursion. Without it, the calls would continue forever and cause a stack overflow. Analogy: Russian nesting dolls. Each doll contains a smaller doll. You keep opening dolls until you reach the tiniest one, which cannot be opened further. That smallest doll is the base case. Mathematical example: factorial n factorial. N factorial is defined as 1 when n equals 0, and as n times open parenthesis n minus 1 close parenthesis factorial when n is greater than 0. Unsigned long fact takes an unsigned integer and if n equals 0, return 1 as the base case. Otherwise, return n multiplied by fact of n minus 1 as the recursive case. Another classic, the Euclidean algorithm for greatest common divisor, uses recursion. Integer GCD takes integers a and b. If b equals 0, return a as the base case. Otherwise, return GCD of b and a modulo b as the recursive case. When designing a recursive function, always first write the base case, the simplest version you can solve directly, then express the general case in terms of a smaller subproblem that eventually reaches the base. In C and C++, the compiler processes source files from top to bottom. If you call a function before the compiler has seen its definition, it needs a prototype also known as function declaration to know the function's name, return type, and parameter types. Without a prototype, you get errors like foo was not declared in this scope. Typical workflow. Step 1. Write prototypes in a header file *h. Step 2. Include the header wherever the function is called hash, include myfunc.h quote. Step 3. Provide the actual definitions in a source file *c or *cpp. The header file myfunc.h contains include guards and declares the function void greet taking a const char pointer name. The main source file includes the header and calls greet with the string Alice and returns 0. The implementation file includes stdio.h, and the header then defines the function void greet taking a const char pointer name that prints hello, name exclamation mark using printf. Header guards, if not defined, define end, if prevent the same prototype from being included multiple times, which would cause duplicate definition errors. This arrangement lets the compiler know about functions regardless of the order in which source files are compiled, resolving compilation order dependencies. Explanation: tracing function calls is a skill often tested in exams. It means walking through the program line by line, keeping a mental or written call stack that records which functions are currently active, their parameter values, and where each will return. Example problem C. Int f left parenthesis int x right parenthesis open brace. If x less than or equal to 1, return 1 semicolon, return x times g left parenthesis x minus 1 right parenthesis semicolon close brace. Int g left parenthesis int y right parenthesis open brace, return y plus f left parenthesis y minus 2 right parenthesis semicolon close brace. Int main open parenthesis close parenthesis open brace print left parenthesis %d backslash n comma f left parenthesis 4 right parenthesis semicolon return 0 semicolon close brace. Tracing steps. Main calls f of 4, push f of 4 onto stack. Inside f of 4, x greater than 1, so compute 4 times g of 3. Before multiplication, call g of 3, push g of 3. G of 3 returns 3 plus f of 1. Call f of 1, push f of 1. F of 1 hits base case, returns 1, pop f of 1. G of 3 now returns 3 plus 1 equals 4, pop g of 3. F of 4 computes 4 times 4 equals 16, return 16, pop f of 4. Main prints 16. Creating a table helps. Table with columns, call level function argument returns. Row 0, call level 0 function main argument dash returns 16. Row 1, call level 1 function f argument 4 returns 16. Row 2, call level 2 function g argument 3 returns 4. Row 3, call level 3 function f argument 1 returns 1. The ability to draw such a table, track stack depth, and compute intermediate results quickly is what exam graders look for. Explanation: many textbook problems ask you to turn a well-known mathematical formula into a user-defined function. Below are 3 classic examples with both recursive and iterative versions where appropriate. Factorial n factorial equals the product from k equals 1 to n of k, with 0 factorial equals 1. Recursive version unsigned long factorial takes unsigned int n. If n equals 0, return 1. Base case return n times factorial of n minus 1. Iterative version more efficient. No stack depth unsigned long fact iter takes unsigned int n set result to 1 for I from 2 to n inclusive increment I multiply result by I end loop return result. Fibonacci f0 equals 0, f1 equals 1, fn equals fn minus 1 plus fn minus 2. Naive recursive version exponential time unsigned long fibrec takes unsigned int n. If n equals 0, return 0. If n equals 1, return 1. Return fibrec of n minus 1 plus fibrec of n minus 2. Iterative version linear time constant space unsigned long fib iter takes unsigned int n. If n equals 0, return 0. Set it to 0b to 1c undefined for I from 2 to n inclusive increment. I set c to a plus b, set it to b, set b to c end loop return b. Greatest common divisor GCD Euclidean algorithm GCD of a comma b equals GCD of b comma a mod b with GCD of a comma 0 equals a. Function GCD takes int a and int b while b not equals 0, set r to a modulo b, set it to b, set b to r end, while return a when b becomes 0 a holds the GCD. Function GCD rect takes int a and int b. If b equals 0, return a base case, otherwise return GCD rec of b and a modulo b. These functions illustrate how a mathematical definition translates directly into code. Declare the return type list, input parameters, implement the formula, and handle the base case. If recursive, they are also perfect practice for writing clean reusable user-defined functions that can be called from any part of a larger program.